Everywhere in your life, there's code. On your computer, on your phone, on the monitor you're watching me on probably right now has code that it needs to do its job. Now, when it comes to your computer, there are multiple layers of code that can all have vulnerabilities. And in this video, we're talking about a vulnerability not in your CPU, not in the layer below your CPU, but in UEFI, the code that actually turns on your computer. And this bug can be exploited to give a hacker access to your computer forever, regardless of if you wipe the OS or even buy a new CPU. Let's talk about it. Also, if you're new here, hi, my name is Ed. This is A Level Learning, a channel where I talk about computer vulnerabilities, cybersecurity, and all that cool stuff. So if you like that kind of stuff or just want to hang out with me, hit that sub button. Now, this is probably one of the craziest bugs that I have seen in my 10 years of offensive security research, mainly because of how low level it is. It's me. All right, cool. Now, this bug is from a security research firm called Eclipsium. I'm going to mess your guys' name up, I'm sorry. But the bug is namefully called UEFI can has buffer overflow, which, I think that's hilarious. It's a very serious bug. It's a very not so serious name. And it's a widespread impact from a vulnerability in popular PC and server firmware. So they go on to, and I'm not going to read this article out, I just want to show you guys that this company has a automated binary analysis platform that found a bug in the UEFI code handling of TPM. So I'm talking about a bunch of different acronyms here. But UEFI is the spec that surpassed BIOS, right? So BIOS was originally the spec for when your computer turned on, a certain number of things had to happen in the code to get the code that runs on the motherboard of your CPU to execute the code that runs in your hard disk, right? Because your OS lives in your hard disk and the BIOS has code that kind of turns on the motherboard, turns on the CPU, and gets everything going. Now, UEFI is a new version of BIOS. It is an upgrade to BIOS that allows a lot of security functionality. Now, one of these is called Trusted Platform Module that acts as a root of security that gives you an assurance that the firmware on your device, on your UEFI motherboard, is not been tampered with, right? It basically says all this code is signed, we're good to go, don't worry about us. Now, the problem with this, just like anything, is even though you have a TPM module on your motherboard, if the underlying code within the TPM is flawed, then you can take advantage of that code and use it to execute code at the level that the UEFI code runs at. And the issue here is that UEFI code runs at ring not 0, not -1, UEFI runs at ring -2. The reason for this is when your CPU turns on, and not your CPU the processor, CPU the computer, it starts in the most secure state. It says, I am powered on, the code that I'm running is trusted, and then as it goes forward in the boot process, it goes into deeper layers where the code is less and less trusted, but it has code inside of it that verifies the lower layers. So from UEFI's perspective, Windows is not trusted code until it verifies the signature of the Windows bootloader. Now, the issue with this bug they found, and we'll go into the details of the bug here in a minute, is that the bug is found in the secure code firmware, which is a piece of firmware by Phoenix Technologies that enables the processor bring up for all of these lines of Intel processors. And you're seeing the lake here. So basically, I think this goes back to like the 12th generation of Intel chips. So it's a fairly recent and fairly widespread piece of code that lives on all of these CPUs. And the vulnerability allows the local attacker to escalate privileges and gain code execution within the UEFI firmware during runtime. This type of low-level exploitation is typical of firmware backdoors like Black Lotus. And I found this very interesting. I didn't realize this, but Black Lotus apparently is a UEFI backdoor, right? So it's basically like if you get code execution in UEFI, you have to write code that lives there and does things. This is supposedly a boot kit that you can buy for $5,000. Like, that seems really cheap for a boot kit. I'm almost considering, like, for content, like picking it up and seeing what it's all about. But the fact that you can grab one of these for $5,000 is suspicious because the amount of work that needs to be done to get meaningful, repeatable code execution at the UEFI level is a lot of work. And anyone doing this for $5,000 is either one, lying, or two, a galaxy brain that has like thousands of these for sale. And that's kind of the speculation in this article, is that they're not really sure if like Black Lotus even exists or if it does the thing that they say that it does, but that's for a different article for a different day. Now, the reason this bug is so pervasive is because it's kind of a supply chain vulnerability, right? Like your computer comes in, you have like your Windows OS on top of it, and you have your CPU that lives underneath that. But UEFI firmware, like it says here, is a critical piece in the technology supply chain. Now, because UEFI stuff is so difficult to write, it is such a complex field of understanding, there aren't a ton of people that are making UEFI firmware, right? Like one of the major providers here is Phoenix Technologies. So when you have a vulnerability in your UEFI firmware, first of all, you may not even know what version of UEFI firmware you have. Like right now, can you name the vendor of your motherboard's firmware? I can't. And then two, if you can, you are likely affected by this because there are so few people that are writing this code. So it's not like when you have a vulnerability in a particular version of JavaScript or a browser, because like you have to be running that browser, using that JavaScript for that bug to affect you. Bugs like this tend to affect like literally everybody. It's actually insane. The nature of the vulnerability is actually fairly simple. So the vulnerability was discovered by Automata. It's this company's automated binary analysis system, which if you don't know how vulnerability research works, you kind of have two ways you can do it. You can do either dynamic analysis where you run the thing and find bugs in it by putting bad data into it through like fuzzing, or static analysis where you just have the code and you analyze the code and find all the code paths that it could go down and find code paths that are inherently vulnerable through the use of unsafe functions like memcopy or strcpy, for example, right? And so a lot of companies have these things called binary analysis systems where they put in the binary, they're able to symbolically emulate it and then figure out automatically, doing almost no work, what code paths could contain vulnerabilities, and then use that to augment human analysis, right? So they say, hey boss, I think I found a path down here that might use a vulnerable function, and then the human comes in and says, oh yeah, you're right, and then they write a report, okay? And so here is actually the function. I believe this is actually Ghidra decompilation output, but effectively what it does here is you have this variable called TCG2 configuration, and in the UEFI firmware, you try to read this variable. Now, note that you only have 8 bytes of memory for this variable in a written data size. If the data size comes out and the error says that the buffer was too small, it will call get variable again on that same variable using the data size that was written previously. So because it detected the buffer overflow, it actually triggers the get variable to be called again, but because it didn't clean up the data size, the overflow occurs, allowing a traditional buffer overflow in UEFI firmware. Now you're probably asking, would Rust have fixed this? The answer is yes, Rust would have caught this because there are runtime access checks on buffers for code that runs in userland, right, as a normal application. It may be the case that a UEFI firmware may not have the bounds checks that the userland code does for performance sake, so Rust may have caught this depending on what optimizations were used in the kernel. And so what mitigations can you take to avoid this vulnerability? You can go and upgrade your UEFI firmware. A lot of people don't do that, which is it's kind of hard to do. And if you get it wrong, you can break your motherboard, which isn't super fun. But yeah, it's kind of an interesting video. I want to talk about the nature of software in that, there's code running everywhere. And when you have bugs that pop up at like these super low levels, the way that they affect the ecosystem is very, very interesting. So that's it. That's all I want to talk about. Really appreciate your time. If you like the video, do me a favor, hit like, hit subscribe, and then go check out this video about a guy that found a 0-day vulnerability in his entire ISP. It affected millions of people. Go check that out. See you there.